Our team has been tasked with creating a line-following robot that will be able to execute a form of travel with a constant velocity. It must also be able to navigate many different forms of turns according to the demand on the track. In addition to that, we are also tasked to program the robot to be able to stop and start simultaneously on a given sign that is being placed on the track. The new additional features that we have to include in this year project is the concept of speed control, in which the robot will be programmed to detect certain colors of the track and alter its speed in relation to the color.
The infrared sensors represent critical components of the design system. They act as eyes for our line-following robot. The infrared sensors allow for differentiation between dark surfaces and white surfaces. Infrared light is emitted from a series of diodes behind the sensor. Light bounces from the surface, and the intensity differs from black and white surfaces. When the sensor rays over the black region of a track, and hence moving off course, the robot will be able to correct itself. The infrared sensors come with challenges. The intensity of one black surface is not necessarily the same with another. Spacing of the sensors greatly affect the robot's smoothness. These problems were addressed by programming the sensors to note differences of values between surfaces, rather than looking for surface-specific values. In addition, spacing issues were solved through a series of tests, determining the ideal sensor placement. The infrared sensor was integrated into the system through analog inputs of the microcontroller.
The installation of the motor bracket in the robot aims to hold the motor in its place during its operation procedures. The wheel will act as the actuator for the force that is being produced by the motor and move the robot in the manners that we program. The difficulties that we are having in implementing the wheel in our system is in terms of how can we find the best wheel diameter to reach the best maximum speed, while at the same time also an excellent stability. In terms of the motor bracket and its assembly, the dilemma that we are facing is in terms of its cost, on whether are we going to manufacture our own design or purchase components from a well-known manufacturers. The approach that we implement into solving the challenge is by finding the best wheel diameter, since when we test the larger wheel, it gives speed but less stability, while the smaller wheel demonstrates vice versa.
The design of our electrical configuration will be in the form of a printed circuit board because it is both space-saving solution as well as an affordable customization. The prototype robot has a PCB that is layered on an electronics chassis. However, the final product design will be updated from this version. From the body, Anthony and I have decided to custom build the body. Currently, I have decided to make a two-plate design which covers the top and the bottom of the robot. This makes the robot ergonomic and aesthetically pleasing. Note that change in the design will be implemented in the future to attain a better efficiency. The only current difficulty present is the final dimension for the end product. This is because our team has not determined the final dimensions. The electrical chassis and the mechanical body of the robot form the basis platform, as they are two key components in its operation.
The motors in our robot are each being driven using a pulse width modulated output via an H-bridge driver IC. The main problems to date have been selecting the best wheel diameter and final gearing in order to achieve our target acceleration as well as top speed. Initially, the robot used a simple proportional only control loop. Unfortunately, this did not meet expectations and has been recently upgraded to a full PID implementation. This new system will require further tuning before delivery of the final prototype. However, the use of a PID loop coupled with corner sensing will give the final release dynamics and stability far beyond that set out in our product brief. The final software task before delivery will be integrating the upcoming RGB detection system. When combined with the tuned PID controller, this will allow us to accurately and reliably detect and adhere to the speed zones as set out in the product spec.
What we have achieved in the past 6 weeks are mainly the infrared sensors, the designs of the bracket, the coding for all the subsystems, and also the design of the chassis. In the upcoming 6 weeks, we will improve by creations of the RGB sensors, manufacturing of the body and also the chassis, the installment of the bracket, and an improvement on the sensors and the wheel as well. Thank you and hope you enjoy the video.